Welcome to section 4.4, where we're going to end this chapter on forced harmonic oscillators by doing some analysis about the amplitude and the phase angle of the steady state. So, just as a quick reminder, we are still talking about the same forced harmonic oscillator that we're looking at. We're looking at this linear model with a sinusoidal forcing function. So the forcing function will be cosine or sine, or it could be some combination. But remember, cosine is just a shifted sign anyway, and vice versa. So really, sine and cosine are mostly the same thing. And we'll talk later in the section about what is going to change if the right-hand side becomes a sine. And remember that P is essentially the ratio of the damping coefficient to the mass, and Q is the ratio, similar ratio, but for the spring constant. And it doesn't really matter, since there's infinitely many equivalent differential equations for different masses, so we're just going to look at this kind of normalized differential equation that has a mass of 1 or has just been scaled or normalized to not worry about the mass, and that's what P and Q are going to represent here. So really what we're talking about is we're going to be thinking about our forced response. So if you remember, our forced response is just going to be our particular solution, which is, as a reminder, a function of t. And that is always going to be of this form. Now, again, no matter whether the forcing function, remember, this over here is the forcing function. No matter whether the forcing function is a sine or a cosine, we can always write the forced response as a cosine, because again, sine is just a shifted cosine, just cosine with a phase shift. So, again, there's a lot of similar words here with forced. Don't get these two things confused. The forcing function is going to be what is happening, what is that external force to the system, the shaking or tilting of the table, the wind blowing on the building. That's the forcing function. The forced response is going to be that long-term behavior of our solution. Forced response, again, is going to also refer to the steady state behavior. Okay, so they will have the same frequency always. The forcing frequency is going to be the same as the frequency of the forced response. But notice that long-term behavior, that steady state behavior, is going to have a different amplitude. Here, we're just looking at amplitude of 1. We'll talk about other amplitudes later in this section. But here, this is going to have some other amplitude. And this amplitude right here is going to depend on P. It's going to depend on Q, so it's going to depend on the damping. It's going to depend on the spring constant, and it's also going to depend on the forcing frequency. All of those are going to matter, right? If we have low damping and our forcing frequency close to the natural frequency, we learned in the last section that with low damping, forcing frequency close to natural frequency, we are going to have a high amplitude. We'll come up with a formula and we'll be able to see that in action. Okay, and then we'll also talk about how we can find this phase shift, this phase angle, which is related to the phase shift. We'll talk about that later as well. This is an introduction talking about what we're going to talk about. That is kind of what we're doing right here. And that's mostly it. Anything else I want to say? Again, we will because realistically, there is no unforced harmonic oscillator. We can get very, very close. We can get very, very small damping, but really, we can't really ever get rid of it all. So this section will talk about how do we analyze what happens if we're almost undamped. And so we'll leave you with this idea, is that small damping, and I'm going to introduce a new piece of notation that you may or may not have seen before, and it looks a little silly. P is much, much less than, or just much less than. All right, so if P is really close to 0, you could have there's kind of like a hidden greater than 0 right here. But if P is much less than 1, then it's going to be very similar, or will approximate will approximate with an undamped, because they're very, very similar. And as long as we really focus on this for finite time, it's going to mostly be okay. So we are not going to want to look at really asymptotic behavior, like super long-term behavior for infinite time, because then, of course, then you will have a difference. But as long as you're just looking at some finite amount of time, if the damping's small enough, we can really get a good approximation just by looking at the undamped, and we'll be doing that. So that's kind of the overview about what we're doing in this section. The next video, we're going to start analyzing the behavior of the steady state, because we're going to solve this differential equation with all the parameters in there. We're going to get some messy things. We'll get a nice formula and use that formula to give us some analysis about how varying some of these parameters might change the qualitative behavior of our system. Anyway, stay tuned. We'll see you in the next video.